Hello everyone! Today we'll talk about the solution to the problem make lexicographically smallest array by swapping elements. This is one of those problems that if you have some experience, then just by reading the title you probably know the solution, but still coming up with a nice way of implementing it is a bit of a challenge. It's not exceedingly difficult, but it's not also super easy, at least it wasn't for me. I had to stop and think for a bit to ensure that I don't get lost in the implementation. Because the reason why it's so standard is that this pattern is very standard. We are given here indices ij, but indices don't matter, only values matter. Well, indices will matter for the final solution, but for swapping two values, only their value matters, and we can swap them if they differ by at most limit. Their absolute value is less than or equal to limit, so they differ by at most limit. Which means that we can swap two values. Of course, if they are within this limit, then great, we can swap them. But also if there is a chain of other values for whom the value is always within limit of the previous one in the chain. So if, let's say, start with the nums of I, and then we can swap it with something else, something else with something else, we could swap, right? And at the end swap with nums of j, then not only can we swap nums of j, this is a very standard pattern, we just propagate nums of I to the side of j, and then propagate the j backwards to the side of I. But that actually also means that we can swap any elements on that chain freely. So this is the central idea. This is a very simple idea. There is no magic here. But if you don't understand it, then try to meditate on it. So essentially, meditate on the fact that you can solve this problem, for instance, using union find. So using disjoint set data structure. By just joining all the elements that differ by at most limit. So as long as two elements can be joined, then everything that can be swapped with one of them can now be swapped with everything that can be swapped with the second one. Everything is just together. There are no complicated situations in that graph. Either everything within a component can be swapped or nothing can be swapped. And now we want the lexicographically smallest array. Another very simple pattern. How do you do something that's lexicographically smallest? You look at the possible options and you do it greedily. Starting from the first position, you take the smallest available option. And this will of course work here. So what is this problem? And that's why I mentioned that it's probably almost apparent from the title. You have some subsets of the original array that can be swapped around freely. Within each subset, values can be swapped around freely. And you want the array to be lexicographically smallest. So you have those sub-arrays, those sets of positions. All those sets of positions will be independently sorted to be non-decreasing, because in that case all of them will be lexicographically smallest, and the final array will also be lexicographically smallest. And this is again this greedy approach. So more specifically, the first position, we have a value that's there and all the values that can be swapped with it. Then certainly we want, when you look at all the positions of those values, the smallest of them should be at the first available position, so the first position in the array. The second smallest in the second available position from that set of positions. And so on, we go over all the elements, so we just sort independently all of those sets. And as I mentioned, you can use union find if you want, or you can use this sorting more straightforwardly. Well, maybe it's not easier, but it's more direct and to the point. But to do it, we'll first of all need, of course, let n be the length of nums. We're going to first take a list of indices, so will be arc sort in it, indirect sort in it. So we take all the indices and we sort them based on the value at that index in nums. Which means that now by iterating over all the indices in this order, we will be iterating over all the elements of the original array in non-decreasing order. And now we have our result. At first we have none at every position, will be because we will be adding values to the result at given positions based on the positions of a single group, which means that we'll be adding them essentially with random access. For this value, indices will be maintaining the indices of the current group. So whenever it's empty, we add the next element in our order, and all the subsequent elements in the order, for as long as they do not exceed the limit, will be in the same group. And this is the position where we'll be adding the result. And now we're going through all the elements in the order. So we take the ith element in the order, we add it to the group, and now either this element will be an element that can still, essentially, its group will grow in the next step and we don't want to do anything, or this is the last element of the group and we have to do something. So when will the group not grow? The group will not grow if this is the last element completely, because we have to finish the final, calculating the final group, or we look at the next element in the order. And that element, we compare it with our element, so we compare the nums for those indices. And if the next element is greater than our current plus limit, that means that we will not be able to swap it with the current element. So definitely will not be able to swap it with anything else in the group, because those values are smaller than our value, which means that the group will end at this current element. So what do? We sort the indices of the whole group, and now we know the sorted group, of course, is just this order, maintains the order of elements sorted in the whole array, and our current group is just all the elements. If we have, let's say, 5 indices, then those are the last 5 elements in order that we've looked at. So we'll have to sort their indices and write them back into those indices in the result, but in the sorted order. So we take j from start to I plus 1 inclusive. So now we're jumping back to the start of the group and going again for all the elements in the group, and we take that element, so we take nums of order of j, and we add it to the appropriate element in the result, which is the appropriate element in the list of indices. So the first, second, or 0, first, second, and so on. So the idea here is simple, it's just that the implementation has many levels of indirection, so it might be a bit confusing, but as I mentioned, when we have, let's say we've seen 5 values, because we are going through all the values sorted, so we have the indices of those 5 values. Looking at the last 5 elements in order from our position I, those are the indices in the original array where those 5 values in the group reside. So we want to go through them in the order that's defined in order, and write them back into the result based on their original indices, but those indices are sorted. So first available index gets the smallest number, second gets the second smallest, and so on. And of course, now we've processed the group, so the group becomes empty, and the starting position becomes one more than the current position that we are looking at. And at the end, we just return the result.